try to cover a bunch of material today, so hopefully we can get closer to being caught up eventually. So share my window. Okay, so let's when we finished up last Friday, we had begun talking about memory-based modulation techniques, which were particularly useful in this case in improving our frequency shift keying type modulation, right? So FSK is the digital equivalent of FM, but when we go from symbol to symbol, there could be some discontinuities in the phase, and so that causes some spectral problems, some bleeding out of the energy, and so we used a memory-based modulation technique to smooth out that and to kind of enforce continuous phase at each symbol boundary. Whenever the symbol changes to a different frequency, we still can maintain continuous phase. And that's, we're not going to, revisit all that complex math and that type of thing, but it's given there to show you an example of memory-based type modulation schemes. Most of the modulation we'll look at over the next couple of sessions are going to be memory-less, and then we'll kind of revisit memory-based type systems later on in the course. Today we're going to look at receiver design, and we've got a few lectures on this and trying to now we've looked at how we can modulate the signals and looked at different constellations, different techniques of modulation. Now we're going to go deeper into how we can a receiver can use its knowledge of the constellation design and try to make the best decisions. But first, I looked at the homework assignment on homework assignment 3. That was the random variables. I think everyone found that pretty easy, and actually everyone got great scores on that. And but I do have a few notes that I want to kind of cover in terms of MATLAB, and I make some mention of Git there also. And then today we'll dive into the function of receiver, the RF receiver block diagram, some channel characteristics and impact, and then we'll get a little bit more mathematical and look at probabilities and look at optimum receivers. And then our next presentation, which maybe we'll get to start that, will really go into some of the mathematical bases of creating or analyzing an optimum receiver. But first on MATLAB, this isn't something that you're going to get points off on or anything like that, but it's just a good practice to always reset your environment when using scripts. So we can use MATLAB in a number of different ways. We can just ad hoc type in commands at the command window and kind of play with different things and hopefully get the results we want. But then if we want it to be repeatable, we're probably going to put it into a script. And that's kind of what I expect with your work, is that ultimately it's in a .m script. And what I would like is your, things that you turn in on your assignment to include your .m file, right? Which most of the time I'm going to be running that, So I download everything from Moodle and I start going through each student's thing, and I run their .m file to make sure that it's producing the results that we want, right? And I'll typically also just kind of look at PNG files. That's real easy to just kind of click on, and I can see a preview. So it's helpful for any charts that you are asked to produce, that you provide them in a PNG format. And I choose PNG because it's portable. That's what it stands for, Portable Network Graphics. JPEG uses a lot of compression, so it's great for images, but it's not really ideal for charts, right? So if you're going to do some professional type presentations, and you want to show some charts, you want those looking as good as you can. So save those, and you can do this programmatically. You put these right in your scripts, right? Which is what I tend to do when I'm working professionally with MATLAB. And so you can put the name of the file that you want to save, and then you can give it a type. And so here I've given it PNG, and then you can also save it as FIG. So this can be your base name, and it'll automatically handle tacking on the extension for you. There's some more modern options in Save As, but it has good backwards compatibility, which is handy because my version of MATLAB that I have licensed with my consulting company is like 2013 or something. So so Save As works, and there's a link in that I provide in the next homework assignment that takes you there, and you can kind of look at that, and you can look at some of the other options that they talk about also. So to back up here a little bit, since we're using scripts, you want to make sure that you don't your script isn't depending upon any particular values or variables being present in the workspace. You might be doing some ad hoc work in a command window, and you think you've got what works, but it turns out that, oh, you forgot to include that command in your script. So if you do a close all clear, close all just closes all your existing figure windows that you might have open. Clear is kind of the important one that clears all the variables in your workspace. And then CLC just kind of clears the screen. That's all. Clear console, I think, is what it stands for, kind of old school. And that way, then when you run your script, you can be assured that everything needed to produce your results is in that script, right? And it's not predicated upon some value already existing. If you clear everything and run it and you get an error, that is indicating that, yeah, you needed that variable or whatever to be declared and set. So then finally, so we started using random number generators, and like I say, everyone did a great job with that. There's different people kind of chose different type of functions in MATLAB. There's the RAND random number generator, and that's kind of the fundamental one. And then things are built around that, and there's kind of easy helpers to do a uniform or a Gaussian, or to do a all-in-one and with the histogram type of thing sometimes. So, but note that there is this random number generator, and you can actually set the seed of this so that every time you run it, you would get the exact same sequence of random numbers, right? So now they're kind of pseudo random at this point, but that would allow you to be able to run it and then get exactly reproducible results. You don't always want to do that, right? So sometimes you want a random seed, and that way you get truly random results. If you're always using a fixed seed and you're always getting the same results, you might be making some incorrect conclusions. So I'm not saying to always do this, but this is something that's handy. So I'm just putting it out there. One can be any thing. I mean, there's probably a range to it, but so that is the seed that you're setting this random number generator with. And then you're also saying, hey, use this twister algorithm, which is kind of a reasonable default choice in terms of what the underlying algorithm is set to for the random number generator. So that's just helpful, handy type of things to help you be more productive in MATLAB. All right, so let's dive into now. A couple of the notes that I want to make is let me pull these up. So if you're using Git, consider using branches to do your new work, but then merge into dev or main, that type of thing. So then that way, when I download or clone your Git repository, I can just use your main branch and that type of thing. When you do give anyone a URL to your Git repo, make sure it's for the repo itself, not like a folder deep in a tree. If you just copy the URL of the web page you're looking at, you're likely to get something that is not exactly what you want. Right, so there's a little button on GitHub to do that. So, and also name your scripts appropriately. That type of thing is just good practice. And finally, on these assignments, just try to make sure you're on time. I didn't take off any points for being a few minutes late. If you are days late, yeah, you're going to get some points off, but you still need to turn them in. There are a few of you all, I think in this last assignment, there were still 3 people that have not turned in this assignment yet. You're not likely to pass the course if you do not turn in these assignments. They're very important. So, and you don't want to fail the course, obviously. So, also, just a heads up, we'll have a midterm on Tuesday, March 5th. And so that's still a ways off, but want you to be planning for that. All right, so back to the lecture here. So let's dive into what the function of a receiver actually is, right? So here, this is a very simple communication system. We've got some data source, and we process that data and to adapt it to the channel. We send it through the channel over some distance, and the receiver at the other end is trying to estimate what the information was that was sent, right? So remember, that's our purpose of a communication system, is to send information, right? To communicate information, right? So, and now when we are doing this, though, the receiver is faced with a number of challenges, right? And I call these impairments. Noise is a big one, and we'll spend a lot of time with that. The signal gets attenuated in some way, depending upon if we're in RF wireless type communication system. We could be on wires, right? Your hardwired network in your office or school or dorm or house. That's a wired network. A lot of us are using Wi-Fi these days, but there's a lot of wired network that still exist. And ultimately, there's wires that run from like your access point to maybe Spectrum's or office, or AT&T's office, or switching center, or something like that, right? So or fiber optics, right? But so all these have different levels of impairment. In some cases, the attenuation is a big deal, right? The drop off of the signal power means that whatever noise you have in the system is going to become stronger and stronger. Right? So this is particular challenge in wireless systems. Distortion, there's a lot of different sources of distortion. We'll cover a few of these. Fading, interference. I know we haven't talked about these yet. I'm tossing these out. We'll look at noise for the next several lectures, and we'll talk about some other of these type of terms later on, right? So the receiver might have good knowledge of the transmitter, but it has a poor knowledge of the channel and the information sent, right? So it doesn't know what the information is. Remember, we talked about how if there's no uncertainty in the information, then there's no need to even have a communication system. You already know the results, right? So vice versa, conversely, the receiver doesn't know the information that's trying to be sent. That's the purpose of the whole system, right? So, all right, so the receiver attempts to learn something about the channel so that it can compensate for its effects and do the best job of estimating what was sent, right? So it typically knows something about the signal from the knowledge of the transmitter design. Normally, when we design a communication system, we're designing a transmitter and we're designing a receiver, right? So in a lot of cases, in these standards, like the Wi-Fi standard or 5G standard with 5G, 3GPP standards organization. So they standardize the transmitter. So if you're a receiver manufacturer, you know what the waveform is that's being transmitted. You can go and download or buy the standard if you need to and look at it, and it tells you all the structure of that that waveform, right? So now, we often actually encode certain structures into the waveform design beyond just the information we're trying to send, right? So we're modulating the waveform with the information we're trying to send to the receiver, but we also include some features into that waveform so that the receiver can measure those. And if it knows what those values are supposed to be, then it can kind of compare what it knows it should be with what it's receiving. And that comparison gives it some clue on the effects of the channel, all those impairments, right? So these would be known reference signals that would be at a certain amplitude and phase and at a certain time in this waveform, right? So now we can try to compensate for a lot of effects, but ultimately we're limited by the amount of noise relative to the signal power or signal to noise ratio. All right, so we've seen this diagram before. Now we're going to start focusing on this bottom part here where our receiver starts here, where we're looking at the results, the things that have come out of that channel, right? And now we're have this digital demodulator, and we're trying to what we're receiving here is symbols, right? So we're trying to estimate which set of bits out here corresponds to the received symbol, right? So we got symbol in and bits out. And depending upon our value of K, that might be 1 bit per symbol, or it might be several bits per symbol, right? And then this channel decoder, we're going to estimate the original bits from a set of redundant bits and implied structure. So it's the kind of reciprocal or converse of this channel encoder. And we haven't talked about those details yet, except the fact that we will add some redundant bits in a structured way so that we can then maybe if one of those bits is an error due to some noise in a channel that affects the symbol that then affects the bits, if we have enough redundancy and we can understand that redundancy, then maybe we can still at least detect that there's an error or even correct the error, right? So that's a channel decoder's job. Then the source decoder, now It's the converse of the source encoder here. We're basically like compressing the signal, trying to take a information signal and compress it such that we can send it in the most efficient manner. This might be a lossy type compression where you kind of lose a little bit of information, but there's a trade-off, right? Or it might be a lossless type of compression where we can get out exactly what was original, right? So these signals would match at this point of the system. And lossy type things, an example would be the JPEG compression algorithm that would compress an image, right? So it's lossy. You can't ever get back completely the original waveform or image. There's other compression techniques that would allow you to get back the original, right? And then finally, we transduce the bits, these signals, back into something that, let's say, a human might be interested in seeing, right? So that might be a voice, audio, or video, or pictures, or something like that, right? So, all right. So here's a receiver block diagram. Now, this is to put things into context for you, right? And here we've got an antenna. There's a little diagram of an antenna here. So we have electromagnetic waves that induce current into the antenna. And then there's some input resistance here, might be 50 ohms in a classic microwave type system. And so that current across that 50 ohms will produce a voltage. Then we filter that using what's hopefully a very low loss filter. And that's designed to pass the band of interest that we're interested in, but kind of reject other kind of nearby strong signals that would otherwise interact with the nonlinearities in this low noise amplifier, right? So to cause some spurious signals, right? So we filter those out. Again, this is ideally a perfect amplifier, but in the real world, it's got a little bit of noise that it adds to the signal. That's why we strive to create a low noise amplifier, right? And so we add the minimal amount of noise while amplifying the signal, right? So then hopefully do that in as linear a fashion as possible, so we don't create these spurious signals. Now here we have a local oscillator. So this is going to generate an RF signal, and that is then going to work with this nonlinear mixer right here to convert the RF signal down to a more reasonable frequency that we can work with, right? And so this is using that same nonlinear mixing that we talked about. We saw a little question on the exam on that one. And looking at the different frequencies, right? So here at the output, you'll have the sum of these two frequencies. You'll have the difference of these two frequencies. And you'll also have a little bit of this signal, a little bit of that signal, and the twice the signals and so on, right? But the ones we're normally interested in are the difference of these two in a receiver, right? And so if this is 2 gigahertz, this processing subsystem might be 10.7 megahertz is kind of an old common IF frequency, or it might be 70 megahertz. Tend to be a little higher these days because everything gets better ability to go higher in frequency. But this frequency here, we want low enough that we can use kind of inexpensive components over here, and but at the same time support the full bandwidth of the signal, right? So if our LTE waveform is or 5G waveform is 20 megahertz wide, then we've got to be at least in that range to be able to process that whole waveform, right? So, and then this filter here is going to now select the exact channel that you want, the exact waveform, and reject everything else. And so we'll look at this a little bit shortly. And then the remainder of the receiver here in this block, this is what we study in this course, right? So, all right, now let's, so that is mostly context, and what we're mostly interested in is what's happening inside here. We've touched on a few of these other things, but most of what we'll study is in this last block here, right? So now, why is receiver design hard? You know, the communication engineers can sometimes get paid a lot of money, and this is why, right? Is because the channel has these impairments, right? So it has some noise, and it also has some phase shift, right? So as you transmit that signal from the transmitter antenna to the receiver antenna, it's going through basically every wavelength of distance. It's going through 2 pi radians of phase shift on its way as that wave propagates from the transmitter to the receiver. And the likelihood of that being an exact integer number of wavelengths is extraordinarily low, right? And so you're going to have some arbitrary phase shift on that waveform at the receiver, right? So what happens there, and this is actually for a laser-based type system, I think, but it just happens to have some really nice pictures, right? So I got it from this paper here. And here we have, maybe it's easier to start over here in the lower right-hand side. So here we have received data with carrier recovery, and what that's implying there is that kind of coherent demodulation where we talked about in the context of the AM envelope detector, where if we don't send a carrier along with the signal, we can't use the envelope detector, and that means that we've got to send we've got to generate a carrier that's at the exact frequency and phase, right? So there are ways of doing that. They're more complex, but there are ways of doing that. So that's been done. That is basically now, since we've matched the frequency and the phase of the signal coming in, we don't have any rotation, which we'll get to in a minute, right? So we've removed the carrier phase uncertainty, but we have noise. Here, our optical signal to noise ratio is 28 dB, meaning that our signal power is 28 dB larger than our noise power. And here we have, let's see, there's 8 constellation points this way and 8 constellation points that way. So that means 8 times 8 is 64. So this is a 64 QAM modulation scheme, right? And you see, even with what's actually a very high signal noise ratio, we still have, wow, some uncertainty. This is kind of a simulated, modeled reception of this data with some noise, additive noise, Gaussian noise added to it, right? And but only a tiny amount, right? And but you can see that, yeah, you can definitely distinguish each of these ideal constellation points, right? So the plus signs are at the location of the ideal constellation points, and you see there's some nice grouping. But if we just drop this by 6 dB, the signal power down to 22 dB, then wow, we're at the edge of being able to make always correct decisions, right? And so our probability of making an incorrect decision like maybe this little yellow spot right there should be this constellation point, but maybe we're closest to that one. And so we'll make an incorrect decision there, right? And same thing with this little green spot over here that's indicating some received symbols that should be here, but are showing up there. When we do a simulation like this, we know what was sent, right? And so we can polarize it based upon what we know was sent. And but in a real situation, a receiver, physical receiver, it doesn't know what's sent. That's its purpose, is to try to estimate what was sent. And so it's going to look at that, and it doesn't know that it's green or blue or purple or whatever. It just sees a signal, and it's only thing it can do is try to match it up with the closest constellation point, right? So this is already being impaired, much worse than 22 dB, and we'd start having lots of errors, right? And here we have, without this matching of the carrier phase, so there's no carrier recovery, and we see that this kind of arbitrary phase uncertainty is causing this constellation to be rotated. So now this maybe green stuff was originally over here, but it got rotated due to some phase, or this yellow was originally up here instead of down here, right? And so that's an impact effect we have to remove also. All right, so that's just without carrier recovery. But even if we do recover the carrier, our local oscillator, remember that's this thing we're using here to down convert that signal. And there might be actually a couple of these in a more complex receiver, but there's oftentimes at least one, right? And so it's going to have what we call phase noise on it, right? And so you'd like it, if it's supposed to be at 500 megahertz, you'd like it exactly at 500 megahertz and never to deviate from that. But it's not an ideal world. And so it will, due to random fluctuations in the physics of the oscillator, have some little minute phase shifts over time, which, phase and frequency are related through a derivative integral type process. And so if you have a little bit of deviation in frequency, that shows up as phase, and phase is a little more sensitive, and that's why we look at it in that way. And that actually looks like frequency modulation or phase modulation, right? And so we see here there's this little bit of phase noise on this local oscillator, and it shows up as tiny little rotations, right? So these rotations are really bad, right? But here, even after we've tried to recover that carrier, we still have some noise, right? So, and this comes through and it is imparted on that signal through that mixer, that nonlinear element that we're using to do the frequency translation. All right, so now let's look at our channel models. And so there's a lot of different effects, but we'll focus on this additive white Gaussian noise channel, which sole effect is that modeling that thermal noise. There's lots of other impairments, but for now we're going to ignore those. We're going to assume that everything else is perfect, but that we do have this additive white Gaussian noise, right, which has this uniform spectral density, power spectral density, and similar to white light, and and it has origins in thermal noise, Johnson noise, right? So our received signal as a function of time is going to be the symbol that we transmitted plus some noise, right? So that noise is also a function of time. It's a random variable, right? So we can write this as a vector, right? Where we choose these orthogonal basis functions and that type of thing, right? So now we can write this as a vector. So we are absorbing the time nature within a pulse in this basis function type of thing, right? So here the SMT is the transmitted signal drawn from the M possible signals, and NT is a sample waveform of a zero mean white Gaussian noise process. Okay, so now let's think back to our lecture on random processes, right? And we talked about how we had those different random noise generators, processes, right? And they would emit some waveform over time, but even the nature of that waveform, which random noise generator we get chosen is random, right? And so we had some random variation over time, but any given situation where we would want to sample that random signal, noise signal, is random, right? So not just variable in time, but also in sample space. Remember that we talked about how we can use the principle of ergodicity to try to simplify that a little bit, right? So just trying to reinforce that concept there. So so here we're drawing a particular sample waveform, zero mean white Gaussian noise process. Now it has this constant power spectral density, and we denote that with N naught, capital N naught, and we divide by 2 because that's kind of how the math works out. And the RT is the received signal. Now, again, this is for this additive white Gaussian noise channel. And we're going to study this because ultimately they're the limiting case, right? So we might have lots of other things, but we can improve that and maybe compensate or eliminate other impairments, but ultimately we're still going to have some noise in our system. So the receiver observes R of T, right, and makes the optimal decision about which message little m was actually transmitted, right? So m could be any of these different symbols that we chose based upon some bit pattern that came in, right? Or we might have k bits coming in. We look at those and we map that to a particular symbol, right? So we showed a 64 Comm constellation earlier where it had 8 by 8 in a rectangular format, right? So each one of those little plus signs in that diagram was one of these M symbols. In that case, M was 64, right? So now what we want to do is we want to make the optimal decision about which message was sent, right? Well, what does that mean? What does optimal decision mean? So it's a decision rule that results in minimum error probability, right? So we can write that mathematically here. What is our probability of error? Is the probability that our estimated choice of M is not equal to the real M, right? The particular symbol that was sent, right? So that's an error probability, right? So if our estimate of what was sent does not match what was actually sent, then that's an error, right? So what is the probability of that? And we use this little caret up here to designate estimated signals or symbols or values to distinguish them from the true values, right? So the receiver doesn't know this. It's its job to figure out what this is. What it's doing is it's making an estimate, right? So what is the probability that it was done right or done wrong. In this case, we're writing it as an error, the probability of error, and that's the probability that the estimate does not match the true value. So let's talk about a general vector channel. And here we've got this vector equation here where R is equal to this symbol or signal that was sent plus the noise, right? In this additive white Gaussian noise channel. M is chosen from this 1, 2, ... up to whatever cap M is for our modulation scheme, according to the probability of sending one of these symbols, right? And then we define this nj here, n sub j, where j ranges from 1 up to cap n, and these are independently, identically distributed zero mean Gaussian random variables, each distributed according to this shorthand for a Gaussian zero mean with a particular variance, which we describe here as this n naught divided by 2, the power spectral density value, right? So that's just saying this is a normal distribution random number variable, random variable, otherwise known as Gaussian, right? So here, this independently identically distributed. So each noise, sample or instant is independent of any of the others, but they're all identically distributed, right? So they would have the same statistics overall. And so if we have n of these, right? So this is a vector, and we've got n of these, then they're all independent, then with the same distribution, then our joint probability is the product of all of these, right? So you think about that joint probability of independent random variables. I know we did a very brief review, but you had a course on probability and statistics, right? So hopefully this is in the memory banks there somewhere, right? So since we're multiplying these things, this coefficient of this Gaussian PDF here, the Gaussian probability density function, the coefficient gets raised to the power of n, right? There's n of these. The exponents in this exponential, these are exponents, and they get summed, right? And that's just through the power of properties of a common exponent, right? So all these are common base, right? So E here is the base, and these are all the same because they're identically distributed, right? So they have the same variance, and it's zero mean, so that mu doesn't show up here, right? But they get all summed up, and so we have this nj squared and summed. So we can rewrite this as the norm of this, these values, right? So these are where the random variable is actually showing up at, right? And so in kind of generic writing of this would be x. It would be x minus mu, but mu 0 is the mean, right? So so this would be a geometric mean, right? So again, conceptual, understand that this noise process is a bunch of different samples, right? Any particular value there, probability, right? So all right, so now let's kind of draw out this transmitted symbols and a channel, and the received signals. All right. Now, in the ideal world, R equals SMM, right? And but the channel adds these impairments. So the channel, which if we can describe the channel statistically, then we can, or probabilistically, then we can write a probability of receiving R given that a particular SM was sent. Right. So the receiving a particular R value given SM was sent. Right. So what did I say up here? The receiver R, the received R depends statistically on a transmitted vector SM through the conditional PDF PR given SM, which describes the random effects of the channel. All right, so the receiver is trying to figure out which M was sent, right? Which M, which would designate which particular SM, right? That's what we're trying to do. All right, so let's introduce what we call this map receiver. So the probability of a correct decision given R, right? So we receive R, and what is the probability of a correct decision? Well, the receiver takes this R value that it receives and estimates M. Well, if this M estimate was actually what was sent, then yeah, that's a correct decision, right? So that's what we want. We don't want incorrect decisions. We want correct decisions. Well, what's the probability of that happening? And can we maximize that probability? Right? So if we have this, this is a conditional, right? So remember that we find the marginal probability or the probability of a correct decision, right? We can integrate that conditional probability multiplied by the probability of R, right? And we integrate that, right? So at each dr, each delta R, we multiply the probability of that particular R by this conditional probability, and then we integrate it for every dr, right? And then that removes the conditional effects of R, and we have what we call that marginal probability. So that's ultimately what we're interested in. What is our probability of making a correct decision in our receiver, and how can we maximize that? So substituting in this information, so we're going to integrate this probability that the estimated M was the one that was actually sent. And so we can now look at this, and we actually don't have to evaluate this integral. We can look at this maximizing this probability, right? And what is the argument? What is the M hat that would maximize this this relationship here, this conditional probability? Right. So again, we're receiving a signal R, and we're trying to figure out what the actual M that was sent. We're estimating this M hat. How do we do that? How do we choose that M hat? So it looks complex, it looks messy, but it's actually kind of a simple concept, right? So we're saying that if we maximize this value, then we'll maximize this overall relationship, right? And so how do we maximize this? We choose a particular argument that does that. Okay, conceptual still. We don't say exactly how to do that, just that that's what we want to do, right? So we want to uh, choose this M hat that becomes the argument that maximizes this, right? That's what the argmax means over the set of M that are allowable, right? So we can write that as also as a probability, the argmax of a probability of SM given R, right? So SM is the symbol that was sent. M is just the index of the particular symbol. All right, so now this is where we, gets kind of cool and really is this map, which we'll get to in a minute what this MAP stands for, right? So we actually prefer to work with the probability of receiving this signal R, this vectorized signal R, given that a particular SM was sent, right? So that's in contrast to here, right? So we're trying to maximize this probability that SM was sent given R. But when we model our receiver, our channel, we can maybe estimate this, right? We can kind of figure out what is the probability that we get this R based upon this SMM, right? If we know how much noise the channel imparts, how much attenuation it uh, affects the SM with, and that type of thing, right? So if we know something about the channel, then we can calculate this probability, right? So that from a simulation standpoint is what we can work with, right? So, but this is what we're trying to kind of optimize, right? So we can apply Bayes' formula here, and there we can flip this relationship around. So now this probability where we're trying to choose the best estimate of M through this argmax process, instead of being this probability of SM given R, we use Bayes' formula, which would then substitute in the probability of R given that SM was sent times the probability of M or SM, right? So M is just an index of the particular symbol, right? So what is the probability that a particular symbol is sent, right? Divided by this probability of R, right? So this is just Bayes' formula or theorem. You can go back and look at that from the random variables presentation, right? So the probability of R is not a function of M. Okay, so I didn't really say much about this, right, in a few seconds ago when I was describing it, because we're going to actually ignore it, right? So since it is not a function of M, what are we trying to do here? We're trying to choose this best estimate of M given all this information here, right? Through this maximizing what is the choice of M that makes this relationship maximum, right? So if PR is not a function of M, then it has no impact over this operation right here. So we can throw it away. We ignore it. And it's only because we're doing this argmax process that we can do that, right? So now we simplified it. We have this relationship. So we potentially, okay, I'm putting that in italics, right? Directly know this probability of what symbol is sent, right? Is what's the probability relationship of all these different M's, 1, 2, cap M. And then we also can estimate or predict the effects of the channel on SMM, right? So if we know how far away it is, we know our antenna gains, that type of thing, we can kind of calculate the amount of signal loss that we're going to have using your EM fields, applied electromagnetic fields, um, and that type of thing. And we can look at our noise in our system and our receiver and figure out what that signal noise ratio is. And that is going to have some effects on SM and perturb what R actually is, right? It'll impair SM and give us this R. And we can, know or predict the effects of that, right? So, we call this the maximum a posteriori probability receiver. I have no idea if I'm pronouncing that right. I've struggled with that my whole career, but it's Latin. So if you look it up in some dictionary like Merriam-Webster, you'll see that it's saying it's inductive type reasoning relating to or derived by reasoning from observed facts. So what we're doing is we're observing this R, right? That's our observed facts, right? And so we observe the evidence and induce the symbol sent, considering the prior probability of considered hypothesis. All right, so this last part, the prior probability, that's this piece of M, right? So what's the probability of the transmitter sending a particular M value, right? So, all right, so that's the maximum a posteriori receiver, MAP. Okay, and now let's consider if each symbol or message M is equal probable a priori. Kind of we know ahead of time that all of the different M symbols are equal probable, right? So if we have K is equal to 3, M is equal to 8, then those 3 bits map into a particular symbol, one of 8. And if we know that those 3 bits are just as likely as any other combination of 3 bits that would be coming from our information source, then we could say that all the symbols are equal probable. If they're equal probable, then through this knowledge of our uniform random distribution, right? So we'd have, these are discrete random variables, right? So M is an integer from 1 to M, but if that's a uniform distribution where they're equal probable, then our probability of any of them is all going to be 1 over capital M. Again, in this case of K is equal to 3 bits mapping into a particular symbol, that requires 8 symbols. 2 to the 3 is 8. So cap M is 8. So that probability of any given one of those symbols, right? The M is referring to a particular symbol being sent, would be 1 over 8. Okay, was that 0.125 or something, right? So, and is not a function of what little m is actually being sent, right? So it's equal probable, right? So they're all equal and therefore not a function of m. If that's the case, then we can actually drop out that piece of m, right? So if we look at this equation here, we've got p sub m times this p of receiving r given that SM was sent, right? And so now p sub m is equal to 1 over m. This capital M is not a function of the lowercase m, So it doesn't come into play in this argmax. Just like we dropped off the probability of R, now we're dropping off the probability of M. But we can only do that if we know a priori. We know in advance that the symbols are all equal probable, right? So we call this a maximum likelihood receiver. We're trying to maximize the likelihood here through this choice of the estimated M, right? But we're doing that based upon our received signal and our knowledge of the probabilities of how that received signal is affected by the channel. So as it turns out, the way we've derived this, both MAP and ML, or maximum likelihood receivers, are optimum, right? So if what we've done here is we're optimizing this choice of the estimated M based upon maximizing this relationship here, right? So but this latter, this maximum likelihood receiver, is only optimum under the more restrictive condition that the signals are equiprobable. If you can't know in advance or can't prove that the symbols are going to be equiprobable, then you should should implement a map receiver. And when you do that, you need to make some estimates of this probability of which symbol was actually sent. Okay, we'll look at some examples of this. Okay, so we've used some Latin here, right? So a priori means from the earlier, and a posteriori from the latter, are these Latin phrases. So this is all from Wikipedia. You can look this up. Or Latin phrases used in philosophy. Okay, as engineers, sometimes we joke about philosophy majors, right? But it's actually, philosophy is used a lot in engineering and in computer and communications in particular. It's also used a lot in AI, machine learning. So, so these are using philosophy to distinguish types of knowledge, justification, or argument by their reliance on empirical evidence or experience. A priori knowledge is independent from our current experience, right? So it's or as part of a new study, we know it in advance, right? So our current experience doesn't really impact our knowledge because we already know it. It's a priori knowledge. Examples include mathematics, tautologies, deduction from pure reason. A posteriori knowledge depends on empirical evidence. So we're doing some observations, we're running some experiments, right? So examples include most fields of science and aspects of personal knowledge, right? So if you're, let's say, a detective, do you use deduction or induction, right? So think about that a little bit, right? So, all right, so that was, don't go anywhere because we've got another presentation here. So let's pick this up. So here, now let's kind of, what do we do with that, right? So that it's probably still seems pretty abstract to you. What does all that mean, right? This map, this maximum likelihood. Well, we're going to now kind of introduce this Q function that has a relationship to the Gaussian function. We'll look at decision areas. We talked a little bit about, just kind of in a hand wavy way, of how we look at a constellation and map a value to maybe the nearest constellation point. Do we always do that? Why do we do that? We're going to look at this, right? And then we'll consider binary antipodal signaling. looks like BPSK, right? So a plus or minus A type AM or PSK type of modulation. And we'll look at optimum detection, and we'll actually get to the point where we can calculate an error probability. So as communication engineers, we want to be able to predict the performance of our systems that we're designing or analyzing, right? So how often will the receiver make a wrong decision on what was sent, right? What is that rate of making a decision where M hat does not equal M, right? So, and under these variety of conditions, and again, we'll focus on this AWGN at first, but then we'll talk about these other channel impairments, maybe finite bandwidth, multipath interference, some of these other impairments that can happen. And and this we'll look at in the context of constellation size and structure. So how can we quantify the probabilities in this MAP or ML receiver? Since we model the noise as additive white Gaussian noise, we can look at the probability distribution function of a Gaussian process, right? That's where that G comes from in this thermal noise or Johnson noise type of situation, where noise would kind of randomly add or subtract, might be positive, might be negative, right? Remember, it's zero mean. We don't really say that in here, but remember that zero mean. So sometimes we might get a little positive voltage, sometimes we might get a little negative voltage or current or whatever, right? And that moves around that received R value to the point where, yeah, the receiver might think it maps to a different constellation point and therefore makes an erroneous decision. M hat, M caret does not equal M, right? So that would be an error. We want to minimize that, right, through this MAP or ML receiver, minimize that error, but we also want to be able to calculate it maybe a little bit, right? So to do that, we're going to use this Q function. So what we're doing is we're actually converting our PDF of the Gaussian, right, where here's our mean and our variance, and we'll normally be working with the zero mean process, and we'll normalize this variance to 1 just for now. And so that's related to n naught over 2, right? So so to then convert from a PDF or probability density function to a probability distribution function, fx, then we integrate it, right? We integrate it from x up to infinity, and that would be our integral. Dang, what do we do with that? Well, here we kind of substituted t in here for x, right? So as a dummy variable. The integral, this integral cannot be evaluated in closed form. So, so we're going to define it here as this q of x, right? And numerically tabulate it, right? So someone else is going to do it. So here we have a Gaussian PDF. Here we have its fx of x. Here we have this q function, q of y, right? So here this actual f of x is this minus infinity to x, right, of the PDF. And we can manipulate this a little bit and have write it as if we swap these, instead of integrating from minus infinity to x, let's integrate from x to infinity. And we know if we integrate this whole thing, we ultimately end up at a value of 1, right? So if we integrate all of this, we're going to go from 0 probability down here to 1 probability out here, right? So this is one of those relationships that we talked about in our random variables presentation. So here we're instead of integrating let's see, this portion up to this value X or Y or whatever, we're going to look at this area and subtract it from 1, right? So then we're going to substitute in this U for T minus M over sigma here. This is our variance, or square root of the variance, and that's our mean. And but then we can also just do this variable substitution in this integral, and so we need to calculate du, and that's dt over sigma. So we substitute that stuff in. It makes that this x here, this relationship right there, and then we can say that our distribution probability distribution function is this 1 minus this q x minus m over sigma, right? And so here's some relationships. This random variable x has a normal or Gaussian distribution with mean of m and variance of sigma x squared. Then the probability of x being greater than some value alpha, right? So that would be equivalent to our lowercase x that we see sometimes, but we're using this term alpha. So now we can write that in terms of this q function of alpha minus m divided by sigma, okay? And conversely, we can say the probability of x being less than some value, right, is equal to q, and we just swap these the numerator around, right? So it's negating it basically. So we can see this, that the q of minus x is equal to 1 minus q of x, right? So these would be related in that same way using this type of relationship there. Right, so some handy things. The q of infinity is 0. The q of minus infinity is 1. It's kind of opposite of f of x because it's equal to this 1 minus, right? So q of 0 is 1/2, right? So it's halfway in between the 0 and 1, right? So some handy things to remember, but generally we're going to look up these q values for a given x value using tables, right? So this table is from the Procus and Stalehi text, which I think is like your alternate text on the syllabus, whereas Lothi and Ding is the primary textbook. And so in Lothi and Ding, it's table 7.2 on pages 471 and 472. They use an expanded table and give you more resolution on the x values, I think. So we can see here that the q of 0 is 1/2. If you start to go larger and larger values, this ends up going very small, right? It's tending towards 0. If you need a negative x value, then you would take 1, and you need to calculate a q of minus 7, let's say, then you would take 1 minus 1.2799 times 10 to the minus 12, right? So, all right. Okay, I think this is a great place to stop. So next Friday, we'll start talking about decision areas and how we can now add some rigor to this idea that if we receive some R value out here, we're going to map it to this constellation point. Whereas if we receive it out here, we'll map to that one. And we'll look at the foundations of that, and when does that apply, and when do we need to do something a little bit more sophisticated than that. So, all right, that's it. Have a great week. Good luck if you're heading off to the career fair. Again, if you did not do great on the exam, please make arrangements to see me during office hours or make an appointment, and I can give you some guidance on how to be successful in the midterm, which is in a couple of weeks. And if you're behind on homework, keep going on it. Turn it in. You won't get full credit, but you'll get some.